Hello. We'll go over a couple of concepts from calculus that you'll will use in this course. This will be just a brief overview of the things we'll use. Actually, just two things. All right. So you all are familiar with functions. So here's the function of x, and a couple of things that we are interested is at any given location at this x, what we want to know um, is the function increasing or decreasing. And so for instance at this point you can see that the function is increasing, and one of the things we want to know is how fast is the function increasing. At this location the function is decreasing, and the rate of change of the function is given by the slope of a tangent line. So the slope of a tangent line is a good measure of the rate of change, and the slope of the tangent line is given by the derivative of the function. Okay. And that's what we're interested in. So for instance, you get a standard laundry list of functions and their derivatives. So I'll write them down. Write down a laundry list for you guys. So and again, like we said, the derivative of the function represents the slope of the tangent line at that x. Okay, so if the function is x to the power n, the derivative is x n x to the power n minus 1. The derivative for ex is the same. That's the only function whose derivative is the same as the function. For log x, the derivative is 1 over x. And here are derivatives of some trigonometric functions. For cosine x, it's minus sine x. The derivative of sine x is cosine x, and so on. And you can find a list online if you choose. Okay. So for instance, if our function is the position of an object as a function of time. So for instance, here's the x coordinate, and let's say here's a particle that is moving, and I'll simulate the motion of the particle moving along like so in time. So this is t1, t2, t3, and so on, t5. Those are the positions of the particle at different times. So this might look something like this. The particle is going to the right as time is increasing, and then going back, and then sort of at rest, and so on. Okay, so if at this time you go to the graph, you draw the tangent line, and the slope of that tangent line is the velocity of the particle. So that's one of the uses of the derivatives. Now on the other hand, if you plot the velocity of the particle as a function of time, the derivative of velocity is the acceleration. Acceleration is dv by dt, which is also the slope of the tangent line on this graph. Alright, so that's what we use derivatives for. Now let's briefly talk about integration. Okay. So let's go back to our function. So let's say fx is a function of x. Okay. Another useful thing for us in physics is the area under the curve. So the area under the curve from x1 to x2, for instance. Okay. And the area under that curve is given by the integral. Okay. x1 to x2. So for instance, let's say, well, I'll make up an example. Let's say you're pushing a box, and the box is moving along the x-axis like so. x1, x2, x3, x4. and let's say the x component of the force at x1, the x component of the force at x2, and so on. If this force is changing, so we'll plot that x component. Now I'm using the same x here, is changing like this. This area under the curve, as you push the box from x1 to xn, so xn, this area is the work you have done on the box. So in our example, I'm going to drop, so this is the x component of the force. I've dropped the subscript x. This is the x component of the force. Integrated from x1 to xn gives you the work done on the object. So that's one use of the integral. Here's another example. So let's say you're playing baseball or something, and as the ball comes at you and you hit the ball, the force that the bat exerts on the ball is a function of time, and the force is a function of time, and so the force is 0 before the ball is in contact with the bat, and as the ball is in contact with the bat, the force can increase to a large amount and then go back to 0. Typically this is about 50 to 100 milliseconds long, the contact time. So, and this area is called the impulse, which is equal to f of t dt, and that shows up as the change in, and now I'm writing down one-dimensional results. That shows up as change in linear momentum of the object. Okay. All right. So again, to summarize, okay. Now, so how do you take the integral of a function? So you know how to take the derivative. So df by dx. So here's a function and here is its derivative, and derivative and integrals are opposite of each other, so you can think of them as inverses of each other. And so what we are saying is, if this is the function, the integral of this function is that. So derivative is going this way. Okay, let me clean this up. Derivative is to the right, and integral is to the left. So for instance, the derivative of x to the power of n is n x to the power n minus 1, and the integral of is x to the power n. Okay. Anyway, you can find tables, so I'll give you a standard table. So f of x, if the integral of this will work out to be, so if you have x to the n, it'll work out to be x to the power n plus 1 over n plus 1. The integral of cosine x is sine x. The integral of minus sine x is cosine x, and so on. So the integral of 1 over x is log x. E to the power x is e to the power x. All right. So anyway, all right. So again, to summarize, there are two aspects of a function that we're interested in. We are interested in, at a given location, how fast the function is growing, or decreasing, and that's given by the slope of the tangent line, and the slope of the tangent line is equal to the derivative of the function. The other thing we are interested in about a function is what is the area under the curve, and that is given by the integral. Okay, that's your basic calculus that we'll need.